All right. Can you hear me and can you see my screen?
Yeah.
All right. Perfect. Perfect. Okay. So it would help if I was at the beginning. All right. So welcome to yet another week of Violent Python. You guys are so close, roughly another 5 weeks of this semester left. So this week we'll be talking about covert communication with images, essentially doing steganography of sorts. So normally I would take the opportunity to go over the assignments for last week. However, we're technically still in that week, so you can expect the video walking through that and sharing of the solution, if you will, Wednesday as well. All right, so let's jump in this. Let's talk about some covert communication. What is this? We can have a layman's term understanding of it in terms of having communication that is not necessarily known, communicating in such a way that is secretive in nature, and all of those would be somewhat right. But from the Orange Book itself, if any of you or CISPs or dealing with things like this, from the Orange Book itself, any communication channel that can be exploited by a process to transfer information in a manner that violates the system's security policy. And we see this quite often from a cybersecurity perspective. Threat actors, they love to communicate in this manner, as you can understand why that would make sense. But really, what is the history associated with this? Well, it dates back to a long time ago, for lack of better words. And really, where does it come from? Well, it comes from the Greek root. So when we think of stegnos, essentially equals covered, and graphy, writing. So when you put those together, you essentially have covered writing. The first use of this were dealing with the Greeks and the Persians, and this was being utilized as a way to communicate secretively and through covert means. So we're talking roughly 4,000 years ago. So looking at this, well, there was a time where an individual was essentially exiled, and he wanted to be able to share information. He decided he needed to be able to get information back about an impeding invasion. And the method that was utilized to be able to do that was to be able to utilize a wax book, which I'll talk about here in a minute. But really, the reason why he was doing this is, things were bad. He was near death, and he wanted to be able to get this information back and to assist. So he utilized a wax book. You could think of this in kind of present day, almost like an iPad for that time. There was a set of wax paper associated with it, and they would write information down within it. And they would do it in such a way to where there was essentially a code answer, if you will, that became what was used to encrypt or hide the information within the data itself. So looking at it, you might not think much about it. However, in the underlying aspect of it, there was data that was being hid. So when we look at the goal of modern steganography, our very own Professor Hosmer, in a publication roughly 20 years ago at this point, he was noted as saying the hiding of data within digital carrier by slightly altering insignificant characteristics of the carrier that does not appear to alter the normal rendering of the data. Now, his take on that is much like everybody else's take on it in present day, right? So you'll see varying definitions associated with this, or understandings of what that really means that is very like what he just said. So steganography is at its core designed to be exploited through human weakness. So why is that the case? Well, we really have two perspectives. From a human sight perspective, well, we have poor detection as humans, and our ability to identify different shades and colors it's horrible. And we have some people that are colorblind, right? But even from a human perspective, the slightest change won't be significant enough for us to be able to understand or be able to point out that change. And the same kind of goes from a hearing perspective. Our stuff is very sensitive to noise, and there's distortion and things that we might not be able to slightly understand if they were to change. And that's why you think about like animals, where there is particularly dogs, why their hearing is so much better than ours, right? So the chance of their hearing or their smell being exploited is a lot less likely than what it would be for us. So in those respects, this is where steganography really does well for us, because what happens is we have digital images that are created by just different types of software. We could think of cameras, scanners, graphic software, and all those other things that really produce images. And there's pixels that are made up within those images. And we have an example on the screen here. So we might have an image of an H. However, there's going to be ones and zeros that are going to represent those pixels. And each one of those pixels is going to be part of the grid. Now, this representation of it might be a 640 by 480 in terms of rows and columns, but from a dots per inch perspective, we're thinking 75. Now, both of those things don't really mean much to you at the moment. And really, aside from the rows and columns, the last piece may not. Really, what we are trying to depict here is for each one of those pixels, well, we have some colors that are being shown there. And when we think of this, the pixels being each one of these blocks, right? When we think of each one of those pixels, we have red, green, blue, or in this case of the photo, blue, green, red. And this is what makes up all the overarching colors that we are most familiar with. So one pixel has 8 bits for each color. So cumulatively, we're talking 24 bits. So each one of these bits, each one of these sets of 8 bits is a different color. And where we get different shades are being able to have these bits on or off. With each one of these on, we get 255. Now we're talking about binary, right? And we're talking from the perspective of each one of these having a representation. So 1 or 0 being off, but their true representation being 1, 2, 4, 8, 16, 32, 64, 128. So if you were to add all of those numbers that I just said up, you'll get 255. If you were to turn off, let's say, this first one, or better yet, if you were to turn off these first 2 to the right, that being 1 and 2, if we were to subtract that total of 3 from 255, we would now have a 252. So with those being turned on or off, they're ultimately being tied to different shades of that overarching color, in this case being red. And from a human perspective, the most significant is all the way to the left, because that is housing 128. So if you were to essentially take off half of it, that might be significant enough where somebody might notice it. However, if you were to take off the least significant bit, which is all the way to the right, that's going to be a 1. And starting that way, if you would, and then that's going to be less likely for the human eye to be able to tell. And that's where steganography comes in. Now, understanding, if we were to take 2 to the 8th times 2 to the 8th times 2 to the 8th, we'd get 16 million possible colors, right? So if we were to change slightly one aspect of it, the human eye isn't going to be able to make that determination. So again, one pixel has 24 bits. That's going to be 8 bits for each one of the colors. All right, cool. So zoomed in a lot more here. We see the same thing where there's 8 bits, total of 24. And this is all going to be from a binary perspective, 1 or 0. 1 being on, 0 being off. And if it is 1 and turned on, then that underlying number associated with it, right? And I mentioned 1, 2, 4, 8, 16, 32, 64, 128. So that's going to be incredibly important for us as we look at this. So again, the least significant bit, that is what we are going to seek to change in terms of being able to hide data. Again, the least significant kind of is self-explanatory in that the slightest change to it isn't going to be noticeable enough from a human perspective, which is why we're going to look to make changes and hide data there. Okay, so let's look at this from the perspective of actually looking at the hex of a file. If we were to parse this file, this BMP file, if you will, we see the first aspect associated with the signature. That signature is that header information that's going to tell us what type of actual file it is. It isn't the fact that it's a .bmp. It's the header, that signature information that's going to be able to depict that for us. We'd have the file length. We see that with the next couple of bytes. We'd see the pixel data offset. This is going to tell us where the data actually starts. We see the width of it. We see the height, the color density. And from this perspective, 1800 or 1800 in hex, that's going to be 24 bits. That's where we're going to get the actual overarching red, green, blue 8 bits per. Now, this is the point where the actual pixels themselves actually begins. And this would have been determined based upon an earlier part of this, up around the 3600 on the first row, telling us specifically where this is going to start. So there's going to be 1 byte for the actual color density, but although 1 byte per, we're actually looking at 24 bits. So 1 byte has 8 bits. And because there's 3 bytes, there's 24 bits. And each one of those is going to weigh into the overall composite of the image itself. So if we were to take this 402020 and then change it utilizing the most significant, or excuse me, the least significant bit, changing it to 412121, well, that again would not be enough for the human eye to be able to make a difference or be able to tell the difference. And to really put it in perspective, it would be this. So the one on the left, the bottom image there is the one on touch. The one on the right is the one that we have altered the least significant bit. And from a human eye perspective, not able to tell that difference. So we are going to be using the PIL, the Python image library, to be able to extract this pixel data. All right. The interesting or really great thing about this is, 1, we've already used it, but 2, this is going to make our life a lot easier in terms of being able to access and alter this data. So we're going to import our libraries. There's nothing new there. We're then going to be able to call upon and create some constants. In this case, red, green, blue. This is so we can help to understand what is what. I'm then going to read in the file, and actually, rather than use this screenshot, I think I can have one more slide here. Let me just fast forward because I am going to actually walk through this. This talks about the assignment for next week. Okay, cool. So within the D2L, you'll see that there is a starter script for you. This is no different than any other week, getting you started here. So I'm going to go ahead and run this, or actually, we'll just step into it. And doing so, I'm going to import my libraries. I'm going to create an index for my tuples here. And then I'm going to utilize image open and point to my image file. In this case, the MonaLisa.bmp is in the same directory in which I am running my script, so I can feed it the relative path. This MonaLisa.bmp is on D2L for you. Now, once I read that in utilizing the open method, I now have that data stored into my image variable. I'm going to utilize the load method from image, and then I'm going to store that as pics. Now that I have that data, I can now start to do a little bit more with it. I'm going to set a baseline as far as my pixels. This is me specifying my row and my column that I want to alter. If you recall, as I pulled up, let me pull it up again. As we had this up, there was rows and there were columns. Where a row and a column intersects, well, then that becomes the pixel that's going to be altered. So I am specifying row 0 and column 0. Cool. Once I have those, I'm going to read that data in, read those pixels in, and I'm utilizing pics, which we have up above where we loaded that information, and then I'm going to feed it the row and column. Here we're using 0 and 0. Once I have that, I then have those pixels, and when I look at this, the pixels at 0, row 0, and column 0 are 128, 96, 64. Okay, perfect. So I'm going to take pixel and I'm going to read in red. And when I do that, well, I've stored that as red pics and I have red. I'm going to do the same thing for green and blue. So at this point, I've specified the column. I then read the data in, and then I parsed out the individual red, green, and blue entries, 128, 96, 64. All right, I'm then going to spit out to the screen the original binary associated with the red, green, and amber, or red, green, and amber, red, green, and blue. Again, if I were to count these, because it's going to be a total of 8 digits, all the way to the right is going to be 1, 2, 4, 8, 16, 32, 64, 128. Because I have a 1 in the 128 column, that makes sense as to why red is 128. And this next one, 96. Well, I have a 1 in the 32 column, and I have a 1 in the 64 column. You add those together, you get 96. This last one, I have a 1 in the 64 column. That's going to be blue, so this is going to be 64. All right, the least significant bit for all of these are 0, all the way to the right, least significant bit. That being said, I'm going to go ahead and create hide as a variable, and I'm going to store 0, 1, 1. This is what I'm going to change my red, green, blue to. Now, this is what I'm going to utilize as my alteration, if you will. So now that I've changed that and I look at hide, I'm going to take what's at index 0 of hide, which happens to be 0. If it equals 0, then I'm going to do what's called ANDing. And that's essentially going to take my subset of binary that I already have, take this ANDing that I want to use, and that's going to help me ensure that that 0 actually becomes a 0. If it's not a 0, in this case, it's already a 0, so ANDing is going to happen and nothing's going to happen. If it's not a 0, because I want it to be a 0, it's going to kick in this else block, and it's going to do what's called OR. This is all bitwise comparisons of sorts. So ORing here with the pipe straight up and down, ANDing with the ampersand. Because it's already 0, it's going to do ANDing, and essentially it's going to keep it as 0. So nothing's going to happen there. Now, this next one, if hide offset 1 equals 0, then it's going to go in and do ANDing. If not, it's going to do OR. We know that index 1 of hide equals 1. So it doesn't equal, 1 does not equal 0. So my if block is not going to kick in. Instead, my else block is, and it's going to do ORing. This is also, I can change that data. So if we look at this, it was already 0, so it didn't change. This one wasn't wasn't 1. So we did bitwise ORin to essentially change that digit to a 1. So now we're at 97. This one for offset or index 2, we see that that's going to be a 1. 1 does not equal 0. So instead of it doing an ANDing, essentially keeping it the same, it's going to do a bitwise OR, which is going to change it to that 1. So now when I look at my blue was 64, 65, and actually let's just print it out. We see what those new digits are. We wanted to change the least significant bit of all 3. And the code that we were using was 011. So when we look at this, red was already 0 for least significant, so that didn't change. We ended up going into the AND block. ANDing isn't going to change that. We then had green, which was 0. We wanted it to be a 1. It ended up going into the OR block, which ended up altering that. And then the last one, the same thing. It was 1. We wanted it to be, excuse me, it was a 0. We wanted it to be a 1. So it went into the OR block as well. Now, nothing has changed with the exception of these variables themselves are the only thing that has changed. If we now want to have that written back to our file, well, this is where we need to do a little bit more. So the next thing we're going to do is we're going to update our pixels as we know it. And when we do that, we can look back at it as not going to be descriptive enough to give us really much of anything aside from being able to see that information. We're going to now save the pixels back to that row and to that column. Okay, so remember we designated or we called upon column 0 and row 0. So now that we've made that change, we're going to save that information back. And we now need to write it to an image. So the image that I read in was Mona Lisa BMP. Again, already in my directory in which I'm running this script, I'm going to save it to a file called Mona Lisa test.bmp. You can name it whatever you want. And if you don't give it the full path, it's going to save it in the directory in which this script is being executed. And at this point, it is done. So if I were to go in here and look at the original versus the one that I altered from a human eye perspective, you're not going to be able to tell the difference. They are 2 different files. And if we were looking at hashes of the file, they would be 2 different files as well from that perspective. We altered the least significant bit because, again, it is the least significant bit. So given that, we have a very fun week ahead of us because you are going to end up writing some code that's going to allow us to not only change this and hide some data, but also revert it back. Now, I just changed some bits. We're going to make some changes to some bits that actually mean something. And I'll walk through my solution for this so that way you kind of have an understanding, if you will. Now, going back and looking at, what we just did here, when we read in our pill library to read the contents of our actual pixels, this data was being stored as a tuple. It wasn't a list. It wasn't a dictionary or anything like that. So I know we haven't talked a whole lot about tuples within here. Tuples are immutable in nature and, are something that we can use to house and hold data. But I wanted to make sure everybody knew that it wasn't a dictionary. It's not a list. The other aspect associated with this is, I can't stress enough how many bits are associated with this red, green, amber 24 bits. And when we look at changing the least significant bit, that's going to be to the right. This least significant bit is going to have a value that it can be changed to of 1. Like we can't put a value of 20 or 99 or something in this field because from a binary perspective, from a decimal perspective, this field can only hold a 1, and the most significant would be 128. Now, the thing that gets exploited here, again, humans, because from a human eye perspective, all of this stuff really looks the same. None of it looks like things that would be something that we could actually note. And you know, I think the other thing that I'll say here is what else? I think we definitely talked about the column, the row aspect, being able to understand that. Again, the image itself is made up of pixels in different rows, different columns. So we were impacting the one at row 0 in column 0. All right, so let's look at being able to hide some data. All right, so I'm going to go ahead and not show all of this because that's going to be a solution that I'll share with you after we get done with it. With that being said, I'm going to go ahead and just run this. Right, and this script's whole purpose is to be able to hide some data. And when I say hide some data, it's going to change some bits, and I'm going to have a message key associated with it. So if the bit at row 0, column 0 is changed to 111 from 000, then that means something. If it's changed to something else, then it means something else. So where do I want to place this random change and alteration? Well, let's do it linear. So I'm going to select L, and from here, I have different messages that I can input. And when I say different messages, they're going to be messages that are hard coded based upon a particular change, if you will. So looking at this, you'll note that we have 8 different messages, because when I look at the different settings that I could have, the different combinations rather, I have 8 different ones, right? So I can have all ones. I can have 110, I can have 100, I can have 100, 011. And each one of those, I am then going to tie to a message, right? So if I change it to all zeros, maybe that means dead drop at something. If I change it to 100 from whatever it is to begin with, maybe that means 12 p.m. sharp. And each one of these things are small things, but when I put them together, give me an overall message. So in this case, I might put in 0. Okay, cool. So it starts off the message and tells me dead drop at. And I might say I want it to be the corner of Madison Avenue. So I'll put in 2, and now it starts to build that message. And I want to do it at 12 p.m. So I'll select 5, right? And this is my message: dead drop at corner of Madison Avenue and East 34th Street, 12 p.m. sharp. Okay. When I selected 0 in the background of my script, somewhere 0 meant change it to maybe 000. And this other one, corner of Madison 2, it might have meant, cool, change it to 010. And then the same thing with the other one. So I'm only limited to 8 different messages that I could hard code and put in. Now, once I've done this, I'm going to say, go ahead and create a new file. So I'll say that, and I'll call it Mona test BMP, and we'll get that written out. And when I look at that, again, it looks pretty similar to the original one, not enough for the human eye to be able to tell. The other great thing about this is it also tells me where I have altered pixels. Okay, so I now have the location of where I've altered pixels. This location, probably this message. This location, the next message. This location, the third message. And now I have an altered image. So part of what you're going to do this week is you're going to do something like this, very much like this, where you're going to create code utilizing the starter stuff that I've already provided that is going to allow you to hide a message. Hide a message. My code book, as you saw within the screen, is going to be what you're going to use for a code book as well. And I've already depicted what you should match them up with. So when a person selects the option associated with drop package and garbage can in the background, you should be utilizing 100 as what you're going to change whatever row and column to, right? 100, for example. Now, once you do that, your code will, just like mine, it should create a new image file, and you can have it spit out the altered pixels. By having the original one and the altered image, you can then put back together, or you can really find what's been changed. So by having the original file and having the altered one, we can figure out what's changed. In doing so, this is where we're going to utilize another piece of code that you're going to write. And this is going to be able to retrieve that information, retrieve that message, if you will. So I already, in this code, have hard-coded the Mona BMP, the original file. I need to feed it the file that has the covert message in it. So I called that Mona test BMP. And what it's going to return back to me is that actual message, because I was able to feed it the original file. I was able to feed it the file that had the covert information in there, and I was able to comb through to be able to understand in the covert file what is different than what is in the original file. Pretty cool, right? So you're able to do this, you're able to make this. There's programs out there that do this for us, as you can imagine, but we're going to be able to do this all utilizing PowerShell, or not PowerShell, although we could do it in PowerShell. We're going to do this all utilizing Python. So what do we have? Again, we have us essentially making this code. You're going to need to be able to employ these concepts, create a simple covert communication capability, utilizing the true image, color image that's provided. That's going to be that Mona file, and that Mona file is in D2L. You'll be utilizing the pill library, and then you're going to create something based upon that actual code book. And that code book is in our lecture, and it is like the second to last slide. And you'll see that code book made available for us. So given that, you'll make that, and it would be probably worthwhile for you to make the script to decode it. However, if you don't, no worries, because all you need to actually do is make the one that's going to hide it. I'm then going to utilize my decode one, or my my script that's going to reveal it, and I'm going to be able to dump your message. So what is the grading going to be based upon? Well, you have the original. You're going to hide a message in there based upon your code book. So when I run your script, it should take the Mona file. It should prompt me for a message to hide, and I'd select an option, kind of like how I did mine, where I might select number 3 to add this message, number 5 to add another message, and then it should allow me to save an image file. Once I save it, I'm then going to go off and try to reveal that message utilizing my script. So you'll create the script that's going to prompt them. Your script should also make the change and allow the user to save it out. And then the test is, of course, can we get the message out? If we can't get the message out, then you got something going on that we would probably want to look into. But that's going to be the actual test itself. So given that, let me see if we got any questions from anybody. Okay, so nothing heard. Well, I'll get this uploaded to D2L fairly shortly. Thanks everybody for joining in. See you next week.